There's more to programs than just running them. A typical compiler or interpreter will run various forms of analysis to look at your program, find out facts about it, and then optimize it or change it around, put it in some form that's going to help it run better or give you more information or help you debug it or do any number of other things. People process programs in all kinds of ways. So we're not going to get too sophisticated here. For one, the language we're looking at is very simple, but it's still worthwhile for us to think a little bit about what would it look like to work with a program in ways other than just running it. So here's one example. Let's say we really wanted to find cases where someone wrote an expression like 0 plus 2. Now that 0 plus isn't doing anything. It's a pretty common compiler technique called constant folding to say, well, look, I know what 0 and plus do together. 0 is an identity for it. I can just turn this into 2. But without running the program, I'm just going to find that 0 plus and knock it off. I just don't need it. Right? And now notionally, there's one less operation for your program to do at runtime, and that'll be nice. Your program will run faster, right? That's what optimization is for. It also happens that your program will be smaller in size, pepito. So how would you do this? Well, your AST is just a tree representing your program, so you'll just have to walk all over the tree and look for cases that have this. So we've written such a function right here. We mostly just wanted you to see it. So let's take a look. We'll look at our arithmetic expression. Say, well, if it's a number, you leave it alone. If it's 0 plus something, then just keep optimizing that something. If it's just a plain old plus, then okay, we'll leave the plus there, but look in the subparts to see if there's anything that we could optimize in there. And the same thing for minus, and the same thing for mult. So here's a term that we saw earlier from the quiz, 2 plus 0 plus 0 plus 1. When we optimize it, it goes away. Cool. Now, you might wonder, in this case, why don't we just return E2? Right? Seems sensible enough. We could just do that. What are we going to get out instead? One of the 0 plus 1 stuck around. Why? Well, let's look. We'd have gotten to this case. That'll match here because it's not a 0 on the left. So we'll go into both parts. This part, the left part, nothing doing. Here, we'll get to an a plus 0. So we'll be in this case, and we'll just return E2. But look, in E2, there's more opportunity for optimization. We have to keep going. So that's why we leave that one there. What if we got rid of this and said, oh, no, it's fine. We don't need to do anything. Just leave E1, E2 alone. Right? You might think that you don't need to write these other cases. In that case, no optimization happens at all. The only way we got to even detect these 0 pluses is by exploring this plus a little more deeply. Okay, I wanted to highlight that fact. This is a toy example of what optimization is, but they get actually quite intense, pretty fancy. That's all I'm going to talk about them. We'll leave it there. See you on the next video.